Okay, fantastic. Well, hello everyone. Thank you so much for joining us from wherever you may be today. We are so happy to be coming together today to talk about ocean tipping points. We'll be looking at what drives them, where the thresholds might be, and how the ocean can play a role in mitigating them. So my name is Ariane Wen. I'm a PhD student at the University of Oxford researching the ocean and climate, and I will be your host today. I am joined by an absolutely stellar panel of interdisciplinary scientists and researchers who I will introduce shortly. But first, I just wanted to kind of tee up the session by thinking about what is a tipping point and why do tipping points matter in conversations about climate change. So, we can think of a tipping point as being a key threshold in a system, beyond which point a very small change will trigger this kind of rapid and self-perpetuating shift between substantially different system states. And what's key about tipping points is that those changes can take place over years, decades, or even centuries when we're talking about the climate, and yet they can take still longer to undo, if at all. So some key tipping points, climate tipping points we're going to cover today include the slowdown and the potential collapse of the AMOC, the Atlantic Meridional Overturning Circulation. We're going to be thinking about our poles. We'll look at the loss of summer sea ice in the Arctic and the potential collapse of the West Antarctic Ice Sheet. And of course, we're going to talk about the dieback of warm water coral reefs. Now, we're also going to delve into the science and the technology with which we make the ocean observations that allow us to actually understand these thresholds and make predictions about future change. And we will also touch a little on the potentials of the ocean for mitigating these current and future risks. Now, we'll hear first from our expert panelists, followed by a panel discussion, and then we'll have time for audience questions at the end, which we will take directly via the Zoom Q&A function. So please do be popping questions in as we go, and we will also get to as many of them as we can towards the end of the session. So without further ado, I will introduce our first panelist and lead author of the 2025 Global Tipping Points Report, Professor Tim Lenton, OBE. Tim is joining us from the Global Systems Institute at the University of Exeter, where he is the chair in climate change and earth system science. Now, Tim has been modelling the biosphere, the climate, biogeochemical cycles, and tipping points for over 25 years, and his work informed the setting of the 1.5 degrees Celsius climate target. He also works with policymakers to assess climate change and nature loss risks and highlights opportunities for positive tipping points to accelerate towards net zero. So over to you, Tim.
Thanks, Ariane. Great to see you all. I just want to focus on one crucial ocean tipping point, and that's the possibility of a tipping point in the Atlantic Meridional Overturning Circulation, or AMOC for short. So it's kind of the Atlantic part of this figure you're seeing, where red is indicating a surface water current, generally warmer than blue, which is a deep water current flowing hundreds of thousands of meters down back southwards in the Atlantic sector. So the AMOC is a description of a kind of the closed loop circulation going like a giant conveyor belt around the Atlantic with northward flowing warm waters. And the important thing about this circulation is we know it has tipping points. It has an alternative stable state where it just doesn't exist, if you like. And it has tipping points between this, what we call the on state you're seeing now, and the off state. And it's tipped about 25 times on and off during the last ice age. And we know that this is a system with self-sustaining feedbacks that creates these alternative stable states. So if you're watching the red surface current sort of heading north through the Atlantic, what it does, that circulation, it actually draws in salt at the southern boundary of the Atlantic. If you drew an imaginary line west from the bottom of South Africa. So that helps keep the waters in the Atlantic sector denser. But also as that warm water is flowing northwards, and I can see it stop flowing for now, but rest assured it's, it's still going in the real system. When you see that what we think of as the Gulf Stream going across the northeastwards across the Atlantic, basically the water as it heads northeastwards is losing heat to the atmosphere, and it's evaporating fresh water to the atmosphere, and that's making the water colder and saltier, and both of those things are making it denser, and that's and the water gets dense enough either side of Greenland, where it says deep water formation, to sink from the top of the ocean or to convect from the top to great depth and drive this overall overturning. But in so doing, it draws in the salt and the density, if you like, that supports that circulation. Now, well, this slides are jumping around, not because of me, folks, but the, sh the short version is warming the Arctic region, which is happening 3 or 4 times faster than the global average, and introducing more fresh water from things like the accelerated melt of the Greenland ice sheet, both act to bring the system towards a tipping point where the surface waters don't get dense enough to sink. Let's go to the next slide. Now, when or could this happen? Well, at what temperature could it happen? This is where it happens in a state-of-the-art climate model at around 2 degrees centigrade of global warming. And I should emphasize it takes maybe half a century or so to feel the full brunt of the impacts which are pictured here. But clearly it can happen in some models at even lower levels of warming than this. And the end result here on the right is showing you the Arctic sea ice making a spectacular comeback in winter, whereby it reaches nearly the Thames estuary in February, which is why on the left you're seeing that the winter decadal climate extremes are minus 20 degrees C and 3 fully frozen months of the year in London, and minus 30 degrees C and nearly 6 fully frozen months of the year in Edinburgh, to give a British perspective. Yet the summers are going to be hotter than they are now in this 2-degree warmer world. So the seasonality of the climate in the UK and in Northwest Europe is radically altered. I would submit that that will be a major challenge to our infrastructure, and in separate work we've shown it would eliminate the possibility to grow crops in the UK. If we just go to the next slide, we get a sense of what it could do to food production worldwide by running a simple model on how it affects the viable area for growing wheat and maize worldwide. And it reduces it by more than a half, is the short summary. But this is because we know already from Earth history that when this tipping point happens, you shift the band of rainfall around the tropics southwards, so you severely disrupt or stop the monsoon in West Africa and in India, which should each represent a humanitarian catastrophe. But in the case of India is why it's gone purple and there's severe problems for crop production, but also the major European crop growing regions, for example, and Russian ones, suffer a mixture of a much worse climate and drying that impairs crop productivity. So that's my 5 minutes to emphasize that this is the kind of climate tipping point that would be an existential risk to our societies. And I think we should be doing everything in our power to avoid. In other words, we need to be doing everything in our power to limit warming well below 2 degrees centigrade and minimizing the overshoot of 1.5 degrees centigrade and getting back to and below 1.5 degrees centigrade with all possible efforts we can as soon as we can. Thanks.
Thank you, Tim. Our next panelist is Dr. Ben Moat, who is the head of open ocean physics at the National Oceanography Centre. Now, Ben is a leading scientist in understanding the stability of the Atlantic Ocean and the risk of oceanic tipping points, in particular through his ongoing RAPID research programme, which uses long-term observations to track changes in this Atlantic Meridional overturning circulation we've just heard about from Tim, and in detecting early warning signs of the weakening of this system, which is so key in regulating heat transport and, of course, climate patterns. So let's hear a little bit more on that from Ben.
Okay, thank you. And thanks for that introduction to AMOC, Tim. So I think this sets the scene really nicely here. So what I'm going to talk about is really how we make observations of this AMOC system. And we are doing that right now. So between the Canary Islands and Florida at 26 North, we have an array of moorings in the water that make observations of the strength of this overturning circulation. And that's been going since 2004. But it's not just the strength of this overturning that is important, it's the amount of heat that actually moves around this planet, as the ocean itself moves vast amounts of heat around the globe. But it's also the nutrients and also the carbon. Now, the subpolar gyre as well. So this is a really important part of the system. But we've been making observations of the strength of the AMOC in that region since 2014 through this big international project, this OSNAP AMOC array. Now, if we just next slide. So to enable, so we've got arrays in the ocean where we can measure the strength of this AMOC, but we also need to look at the different changes that are happening because the subpolar gyre itself is very, very complex. As Tim mentioned, we've got that ocean, that dense ocean water being mixed down into the deep ocean. There are lots of sort of boundary currents around Greenland, the freshwater melt that's coming in. So we can't make those observations just through the arrays themselves. So we need to use other means, other observations. And one of these is the Argo array. So here you can see 4,200 robots really floats in the ocean. They float around with the ocean currents. They make measurements of the temperature, the saltiness of the water, and also the pH and the oxygen levels as well. And they report that back every 10 days. And that helps us really understand what's happening within the subpolar gyre and globally as well. So next slide. So what's the current state of the AMOC now from the observations? So this is the strength of that overturning between Florida and the Canary Islands. And what you can see on the vertical axis is the strength of this circulation system. And then we've got the time since 2004. As you can see, the sort of average strength of it is about 17. Now, this is 17 million cubic meters of water per second heads northwards, and around 32 million cubic meters of water per second head northwards through that small gap between Florida and the Bahamas. So here you can see we put a trend through this time series, but no, it's the early part is sort of heading down and then goes down to 2009, 2010, where we had this dip. So it tends to go down. And then if you look at it, 2010 to 2018, it's gone back up. And then it seems to be going down again. So this trend that we put through the time series, you can see here, 0.9, it's weakening at 0.9 Sverdrups, or this million cubic meters of water per second per decade. Now that actually agrees really well with an ensemble of the climate models. They're predicting around 1 Sverdrup per decade. So is this, is this the job sorted? Well, no, because we need caution here. Because as I mentioned, you can look at the early part, the middle of the part, they're going in different directions. So to really understand this weakening behavior, we need to observe for longer, really through to 2035 to 2040, so we can really determine the trend out from the decadal signals, the sort of planetary variations. So if we can go to the next slide. So here I'm just going to give you a flavor of what we can actually see within the observational record that we have from 2004. So we had this one event in 09 and 010 where the AMOC actually reduced and virtually stopped for a very short period of time, and then it started back up again. But during this time, so the AMOC, as Tim described, brings a lot of heat towards the UK and Europe, but the AMOC reduced 30% of that heat supply did not arrive into Europe. This actually meant as well, we had a 13 centimeter sea level rise in New York because the currents weren't as strong, the ocean currents, so they weren't moving as much water offshore. And then just to the final slide, and just those impacts. I think Victoria's going to talk more about this within her presentation, but just to give you a flavor, through that 09-10 event, we experienced within Europe really bad winters, 09, 010, and also 10 and 11. And in the UK itself, 10, 11, it was the coldest since 1910. To put a figure on that actual, the loss or the loss of revenue, and that was estimated around 13 billion. So sorry, Ari, I think I've gone over my 5 minutes, but thank you.
Thank you, Ben. It's really interesting to see how these kind of impacts will see differences in our climate just from these ocean systems. I will now pass over to our polar representative, Dr. Louise Syme, who leads the Ice Dynamics and Paleoclimate team and heads the Earth System Modelling Group at the British Antarctic Survey. Now, Louise is a specialist in polar climate research and studies ice sheets, sea ice, and climate change on seasonal to multi-millennial timescales. And in particular, she focuses on past tipping events and looking at just how accurate climate models are in predicting both polar and also global tipping points. So, Louise, over to you.
Thanks for the kind introduction. Yeah, so actually Tim's already very helpfully mentioned this. So in some sense, what I'm going to talk about is the evidence that the Earth goes through these very major tipping events. So Tim mentioned that there's been more than 20 very large tipping events, which we usually refer to as Dansgaard-Oeschger or DO events. We know about these primarily from ice cores, particularly Greenland ice cores. And we see them in all of the Greenland ice cores that cover this time period. So the plot on the bottom is just showing you a time series from about 60,000 years ago to about 22,000 years ago. And what you're looking at is 3 time series from 3 different ice cores, which all basically show you the same thing. It's showing that the temperature in Greenland and actually the associated sea ice is undergoing a massive reorganization, and that's happening extremely fast. That's the big jump ups, which are marked with numbers there in that plot. So we know that these events can be up to about 16 degrees in Greenland. And we know that they can happen really, or they do happen very quickly. It's a bit hard from the ice core to tell exactly how quickly, but it looks like it's within 20 years. So these are really abrupt, enormous reorganizations. Next slide, please. So these were discovered, the Dansgaard-Oeschger events, in the sort of 1980s. We started getting good ice core records from them. But it's only been rather recently, I would say, that the climate modelling community and the climate community at large has begun to sort of agree on what's really going on here. What is the mechanisms that's causing this tipping event? And actually, until about 10 years ago, we didn't actually think that our climate models were capable of capturing this sort of tipping. Because we hadn't, it was probably partly because we hadn't run the climate models for long enough, because they need a long time to come into the state where this occurs. But we do what we have now found is that there's at least 6 climate models which show very similar behaviour. And the plot there, or the picture, is just trying to give as simple as we can manage overview of what's happening. So at the top and the left, you're seeing a picture where there's extensive sea ice over the North Atlantic. And then during this period of time, there's sort of a build-up of heat in the North Atlantic at depths, but that's prevented from melting the sea ice by this halocline. So you stay in a cold state for a long time. And then at some point, we seem to reach a threshold, and then we may need some noise in the system, but we reach a point where you've got enough heat and enough salt in the North Atlantic that something then triggers that to start mixing up. So at that point, that's a sort of middle plot on the left-hand side. Then you've got this warm, saltier water which is coming to the surface, and effectively convection restarts. So you start forming deep waters again in the North Atlantic at this point. Some of the models show this as a massive hole in the sea ice, which we'd call a linear. Not all models show this exactly the same way, but they all show something similar. And then once AMOC has restarted, as Tim already mentioned, that helps transport salt to the north, and that's a sort of positive feedback that keeps the whole thing moving. During glacial climates, so we then effectively move into a situation on the right column there, where you then tend to have gradual cooling in the climate system because you've got low CO2. So that can actually help sea ice grow gradually in the sort of middle picture there. And then at some point we can then again have a sort of positive feedback where the extension of the sea ice helps begin to shut the convection off. It seems to be what's happening. Then you get less salt coming into the North Atlantic, and you effectively can re-shut the AMOC off again. So we don't think that this is exactly the same as what's happening or potentially could be happening at the present day, but some of the mechanisms are similar. And what it does mean is, because we can see you've got DO events in ice cores, and also from other evidence like stalagmites and marine cores, we have quite a good evidence base to test our models against. So if we go to the last slide. So I won't try and go through this in detail, but I just wanted to emphasize the point that whilst DO events seem to sort of kind of get kicked off in the North Atlantic, and I would argue they are primarily a sort of ocean sea ice coupling, they really are global in nature. So once you have this sort of tipping point triggered, there's a cascade of further changes in the globe. I think Tim mentioned at least one or two of these as well. So we can see from them like the impacts that can occur when you have an event of this magnitude. And the things that I like about them is that they give us a really brilliant opportunity to sort of establish whether climate models can actually accurately capture tipping, because tipping we talk about in the future is hard to know precisely what it will be like, and therefore it can be hard to know whether your climate models are capable of capturing that. By using these data sets and our understanding gained from tipping in the past, it means that we can really have a close look at how good our tools are. And we can also, of course, compare between the different types of observational data we have and between the different models, whether the models tip at the same thresholds, and potentially also whether they show the same type of early warning signals. So I think they're really useful data sets, and I hope it's useful to know something about that. I'll stop there.
Fantastic. Thank you, Louise. So I'd now like to introduce Professor Alex Rogers, who is the Deputy Director of Strategic Science Programs and Partnerships at the National Oceanography Centre. Now, Alex is a marine ecologist and has been exploring the biodiversity of deep sea ecosystems like seamounts, hydrothermal vents, and cold water coral reefs for over 30 years. And he looks at how we can mitigate human impacts on deep sea ecosystems and conserve deep sea life. Now, Alex also works to develop policies around marine ecosystem management and conservation, particularly with regards to biodiversity. So, Alex, would you please tell us a little bit more about these biological tipping points in the ocean? You are on mute.
Thank you, Ariane Wen. I'm going to particularly focus on coral reef ecosystems to start off with, and then essentially look at some other systems as well. So I think most people in the audience will be familiar with mass coral bleaching. This is an event where the corals lose their symbiotic algae, which essentially provide them with nutrients to live. And if that state persists for a certain amount of time, then the corals actually die. And of course, the framework that they formed starts to disintegrate. Now, this process has actually been found to be very complex. It involves the entire holobiont, so the coral and its symbiotic algae. When water temperature goes above a certain level for a certain period of time, which we measure by something called degree heating weeks, this is the amount of time that a temperature anomaly lasts for, then that triggers this mass coral bleaching event. It involves the generation of reactive oxygen species within the coral tissue by the symbiotic algae, and that causes widespread damage in coral cells, which involve a number of the organelles within those cells, so mitochondria, the endoplasmic reticulum, and so on. Next slide, please. So actually, I believe we crossed a tipping point with respect to coral reefs in the late 70s to early 80s. And this was the point when warming of the ocean reached a trigger point for mass coral bleaching. So the occurrence of bleaching at the scale of whole reefs. And you can see here, this is an image from NOAA Coral Reef Watch, which is used to alert us to bleaching events. This is from January 2023 to April 2024. So you can see here where the kind of dark reds and purple colors represent ocean temperatures, which are likely to trigger that bleaching event. If you look at the graph on the left-hand side, you'll see when these early mass coral bleaching events took place. So we saw them starting to occur in the 1980s. But then we had a very large event in the late 1990s. And subsequent to that, we've had a number of other events, 2005, you can see here, 2010 and so on. Where we're headed now, unfortunately, is to a point where mass coral bleaching is occurring every few years. And this was predicted quite some time ago. And this is the point where coral reefs are really being impacted very regularly by these mass coral bleaching events, which means that their time period for recovery is becoming more and more limited. Next slide, please. This is really important. It has major consequences for marine ecosystems, but also for the ecosystem services that coral reefs provide for humans. We know that coral reef fisheries, for example, provide livelihoods and food for about 500 million people, and about 850 million people live within 100 kilometers of coral reefs and are in some way reliant on the ecosystem services they provide. But for marine ecosystems in a broader sense, the destruction of coral reefs is extremely serious. Coral reefs provide habitat for many other organisms. Something like 25% of all marine fish live on coral reefs. They provide protection for coastal ecosystems, and that includes protection for human infrastructure. So the loss of coral reefs potentially makes coastal ecosystems much more vulnerable to other climate-associated events, such as storm surges, hurricanes, and cyclones. So this is a tipping point, if you like, which has, as with AMOC, many other potential consequences, both for the marine environment, but also for humans. Next slide, please. So this is a graph from a paper by Jean-Pierre Gattuso et al. In 2015. And here, scientists applying observations that have been seen to that point in time really looked at the potential for ocean warming and other climate change impacts on the ocean to affect marine ecosystems and particular groups of marine organisms. So you can see here warm water corals being seriously affected from 1 to 1.5 degrees upwards. But by the time we see warming of 2 degrees or so, then these ecosystems are in really serious trouble. But it's not just coral reef ecosystems, it's also seagrass beds and ecosystems like mangroves. Now, the mechanisms here may differ slightly with seagrass beds. Certainly ocean temperature is having a negative impact. And although those systems are more tolerant than coral reefs to ocean warming, at some point in the future, they are also going to be very seriously impacted to the point where recovery will be difficult. But you'll also see here specific groups of organisms, pteropods, which are a type of pelagic mollusk or snail, which are important intermediate steps in ocean food webs. Bivalve mollusks, these are things like oysters and mussels, an important food item grown through aquaculture, krill, and of course finfish fisheries as well. So with that, I will stop there and we can move on to the next speaker. Thank you.
Thank you, Alex. That was fascinating. I don't think people think about us having passed tipping points as far back as the 80s, so thank you for that. I would finally like to introduce our last speaker, Professor Victoria Speiser from the University of Leeds. Now, Victoria is a professor of climate politics and computational social science in the School of Politics and International Studies, and has contributed to both global tipping reports this year and in 2023. Now, she's going to talk to us today about her work assessing the cascading societal and systemic risks of Earth system tipping points, such as the subpolar gyre and the AMOC, and also explore our options in governance approach and strategies. So without further ado, I will hand over to Victoria.
Thank you very much. Yeah, so in my talk, I will focus on the SPGs, the subpolar gyre and AMOC, for which we wrote up a case study in our latest Global Tipping Points report. Tim has already briefly showed the impacts that the AMOC collapse would have on the global food production. So we can see here those two maps again in slightly different colors. But here is also a map for SPG collapse and the kind of projections that it would have on food production. The map shows modeling results comparing minimum growing season lengths in pre and post collapse in an SPG collapse scenario mapped over crop growing locations. With darker shading kind of representing larger reductions in this measure in the minimum growing season length. And so what we can see here is that even the kind of less dramatic SPG collapse would reduce food production capacity, particularly in the northern regions already, which of course has also more global implications as well. Next slide, please. So the reduction of our capacity in growing food would, of course, inevitably result in inflation of food prices. And this is where direct impacts then start to trigger cascading impacts. So inflation and higher food prices could then further cascade into political destabilization, social unrest, and conflicts, particularly where societies are already fragmented, extremely unequal, or where institutions are increasingly weakened or have lost trust. We have also discussed the potential implications for infrastructure. So infrastructure in some of those affected areas have not been built for this drastic ecological regime shifts. And the intensifying and recurring storms would likely result in severe infrastructure damage or even infrastructure loss in some areas. The increased likelihood of storms and flooding would more likely result in direct impacts of property loss and in the long term, potentially even in settlement loss, for instance, at the US East Coast, and more generally kind of accumulating asset loss as well as life loss, which further kind of implications for financial stability and so on. And if whole areas become increasingly hostile to human civilization as they no longer allow food production, as they're increasingly hit by severe weather extremes, people will, of course, then start to move, right? So we will likely then see migration patterns emerge. And in the report, we kind of emphasize that it's important to translate the risks from tipping points crossing into risk currencies, so that resonate with policymakers. And this is why we discuss those implications of crossing tipping points in terms of those cascading risks of food security, water security, human security, energy security, economic stability, national security. But we need to, of course, to emphasize also that there are great uncertainties around those societal impacts. We have already a lot of uncertainty around those Earth system tipping points themselves, as we have, as for instance, Ben Mote has discussed, right? But if we then go to the cascading impacts at the societal levels, those uncertainties become even, stronger, right? And in a way, we are dealing here with several kind of coupled complex systems and their interactions, and it's very difficult to model and kind of try to estimate kind of those impacts that those couplings of those complex systems would have. And yeah, much more research kind of needs to happen. But, and then to my next slide, please. We do know, I think, enough for anticipatory governance approaches and for us trying to kind of know to find responses to those potential great risks and those cascading impacts. And we do have governance options, right? So, of course, preventing the crossing of SPG and AMOC tipping, and of course, of all the other Earth system tipping points should be the absolutely primary governance target and goal. And this requires, in the first place, accelerated mitigation efforts and carbon removal efforts. The potential proximity of an SPG collapse, particularly for Europe, should kind of, basically make European governance and the EU revisit and update their national and the European climate risk assessment, their adaptation and preparedness plans, and their policies and institutions to account for those, potential impacts of such tipping processes. But also across the globe, we need to revisit kind of policies, climate risk assessments, and our plans to account for potential impacts that an AMOC tipping could have. And this, of course, requires, in the first place, shortening the net zero timelines and immediate investment in the development and scaling of sustainable carbon removal technologies. So climate mitigation efforts should be accelerated, and we need to minimize the temperature overshoot of 1.5 degrees to minimize those risks for SPG, the AMOC tipping, and of course all the other Earth system tipping points. So that should be always the priority, and I think we will then discuss more about this in the discussion rounds. Thank you very much.
Fantastic. Thank you, Victoria, and thank you all for those fantastic introductions. So we'll move on now to a panel discussion. This is just a reminder to those listening that you're more than welcome to start popping your questions through on the Q&A function, and we will come to them a little later on in the session. So now we're up to speed on a few of the key kind of ocean tipping points we're facing and what these might mean for us. I would like to put a question to the panel, which is just to ask, how close are ocean systems to these known tipping points under our current warming projections? And what kind of early warning signals do we have that will indicate to us that that risk is increasing? So I think we'll start with Tim, if you would like to take us away on that.
Sure. Yeah, so well, Alex emphasized that the corals might have passed a tipping point a long time ago, and we've stated in the latest Global Tipping Points report that we think that they've passed a tipping point just recently, in the sense of being, a majority of them committed to a kind of a long-term irreversible degradation. And that's on the basis that in the last couple of years, we've seen global temperatures reaching or exceeding 1.5 degrees C. We've seen, as Alex showed, unprecedented heat waves, bleaching and dieback of over 80% of reefs. The rest of the ocean tipping points may not be here yet, but we've heard about SPG, subpolar gyre. So that's referring to one of the two main regions of deep water formation in the North Atlantic. And we think that the collapse of that region, of the stopping of deep water formation there, would typically in the models happen before the other region switches off, which is in the Greenland, Iceland, Norwegian seas, so kind of north of Iceland. In some models, they would say it's already happened. In reality, we wouldn't say that, but it could be close. And when deep convection stops in the subpolar gyre, that can have quite rapid consequences. Some climate adjustments on a decadal timescale of the kind we saw. And how close is the AMOC tipping point? Well, in the latest report, the experts of the case studies say we can't rule out that it might already have been passed, and we just haven't started to convincingly detect the consequences. That would be the worst case scenario. But there's clearly quite a large uncertainty range. I showed you models where a model where it happens at 2 degrees centigrade. There are several where it happens. It can happen at a lower level of global warming. There are some where it happens at a higher level. What I can tell you is when you look in the latest state-of-the-art climate models, that AMOC so this sort of collapse of deep water formation in both of the regions seems to happen in the majority of the models we've looked at systematically at some level of warming. So yeah, that's an alarming result. Clearly, we would like to get more specific information. So just quickly on the early warning signals, the one that several groups, including my own, has looked at is a general signal that before a tipping point, a system will get more kind of sluggish in responding to the little shocks it gets from the world, because that means the damping feedbacks that maintain the current state of the system are getting weaker. And at the tipping point, they disappear and some amplifiers take over. That signal of loss of resilience, we would call it, that's been seen in the fluctuations of the AMOC and its sea surface temperature fingerprint, as we call it in a kind of nerdy way. We find that signal also when we try to isolate variability of the subpolar gyre in models before it tips, and also not so clear whether we've managed to isolate that in observations yet. But clearly there's some evidence consistent with at least heading towards these tipping points as predicted by the models.
Yes, thank you, Tim. Ben, is there anything you would like to add to that before I pass over to Alex and Louise?
We could just tip in that I don't think we've said yet about the tipping points of subpolar gyre and AMOC, because they are different and they will work on different timescales as well. Because the AMOC will feed into the subpolar gyre region, and also changes in the subpolar gyre region will then feed back on the AMOC. So they are this very, very complex, wonderful coupled system. But potentially you could see changes. And so we are observing AMOC at 26 North. But as I've said, we need to keep going on for longer to really try and tease that signal out of potentially the planetary signals. But the subpolar gyre is far, far more complex. And as Tim is saying about the models, we work together to understand this big problem. And so I will talk to the modeling community, and hopefully they'll tell me, well, where do you need to measure? And so we can then put this into place to because with observations, we can't measure everywhere at the same time. So where do we concentrate our efforts? So yeah.
Thank you. And we're going to talk a little bit more later about actually how we do make those observations. First, Alex, would you like to add anything from kind of ecological point of view in terms of those tipping points?
Yeah, I mean, in terms of the reef tipping points, as I said, I feel we already crossed one where mass bleaching started to occur. But as Tim has said, we're now entering a second phase of that, where coral reefs are now bleaching at such a frequency, once every couple of years, that they can't recover, and we're seeing successive degradation of those systems. Now, what to do about this is quite a puzzle, because there is no one answer. Obviously, reducing emissions is critical, but even after that, we're going to have to pull CO2 out the atmosphere to try and get global temperatures down. We have to think about coral reef resto, perhaps genetic manipulation of corals to make them more thermotolerant. And then, of course, there's all the other ecosystem components as well. And in some senses, this is kind of like toppling of dominoes, in that coral reefs actually provide coastal protection for other ecosystems like seagrass beds and mangrove forests. So if we lose the structural integrity of those of the coral reef ecosystems, then we potentially also start to lose seagrass and mangrove forest ecosystems, simply as a result of increased exposure to extreme weather events.
Fantastic. Thanks, Alex. And I'll just pass on to Louise now. How close do you feel we are to those in our polar cryosphere, if you like?
Well, I think the other panelists have answered very well that for the North Atlantic and for the corals as well too, of course. But I'll just touch on, because nobody else has so much, the Southern Ocean and Antarctica as well, because obviously the other main region of deep water formation is around Antarctica, and the Southern Ocean is super important to the global climate. Partly because so much of the carbon that we put in the atmosphere is stored in the Southern Ocean, and it also performs other really important sort of ecological functions for the planet. And if there's significant changes in the Southern Ocean, then that, of course, potentially sets the scene for major changes for the Antarctic continent and the loss of Antarctic ice, at which point we have to start considering very, very major sea level rise. So I thought just while we're talking about thresholds and such, like, it is worth just bringing up that in addition to the changes in the North Atlantic and with the AMOC that have been measured, just in the last couple of years, the picture for the Southern Ocean and the Antarctic region has really radically changed. So up until about 2016, it did seem that not a lot was going on around Antarctica and the Southern Ocean. And then in the period from there, we've had two very major losses of Antarctic sea ice, the second of which occurred in 2023, was really enormous. I can't remember off the top of my head the numbers, but it's sometimes being referred to as a 5 sigma event. It's so large that almost no climate model shows anything like this, even throughout all of their runs. So it's very hard for us to work out both what it's telling us and how likely it was. So it's really, really big changes. So we know there's ongoing changes like that. What is harder to know is what the important thresholds are for triggering really important tipping, particularly for the Antarctic ice sheet. It's also quite hard to know actually for the carbon system as well too. But for the Antarctic ice sheet, we already know we have reached some smaller regional thresholds where we've lost ice shelves. So that seems to be potentially happening now. But in terms of the very large ice shelves, or some of the ones where if you lose some of the bigger ice shelves, that's the floating tons of Antarctic ice, which help provide, if you like, back pressure to stop the rest of the ice flowing into the ocean. For those, it's quite a difficult problem to know precisely what the thresholds are. But the fact that we've already started losing some of the smaller ice shelves does suggest this is certainly something that we need to have very much in mind, in addition to the AMOC, when we're considering how close we are to the thresholds. And some studies would say that we may already be really, really quite close to the threshold for major Antarctic ice sheet loss into the ocean.
Thank you. Thanks, Louise. So we've just touched there on kind of how important it is that we have these monitoring strategies and observing systems that in place for detecting these early warning signs. I'd like to go a little deeper into that. Perhaps, Ben, you can start off talking a little more about these ocean observations and how we go about making them over these kind of such long timescales.
So I think, yeah, I've already sort of touched on the sort of the systems we have in place. So we have the arrays spanning the Atlantic, rapid, OSNAP. They can tell us about the AMOC decline. We have the global, this big international global Argo system with the floats that can tell us every 10 days about the information that comes back. We have ships, we have satellites. But I think what we really, really need is where do we observe? If we want to design an early warning system for a tipping point, say subpolar gyre, where do we concentrate all our efforts? So as part of the projects we work on, the working with the modeling community, where do we make those efforts?
Thanks. In that case, then, Louise, could you tell us a little bit more about those climate models in the polar regions and how accurate they are?
Are you interested particularly for the North Atlantic in terms of that? So I can say a little bit about that if it's helpful. I mean, I mean, one of the reasons I find it really so helpful to look at the past is just because it is a really hard problem. Otherwise, to say, are your models doing tipping correctly? Because yeah, we don't really have enough information about in what order and at what thresholds tipping will be happening in the future. Apart from some of the smaller tipping events which have happened. So yeah, we what we would like to do, what I would like to do, is to be able to test all their current climate models for these large tipping events in the past and see if they actually can reproduce these. The problem with why we can't and have not fully done that is that most of these climate models are now several millions of lines of code long. The ones in the UK will often not be able to run at more than a few years per day. If you can get more than 10 years of model simulation run per day, you're doing reasonably well with some of the most up-to-date current UK climate models. They're very physically, like the way the physics is in them is very detailed, and it's an excellent, like, I mean, it's basically all our foremost experts in climates. It's their view of how these systems should work. So when you write this into a model, you just end up with something that's very large and very complicated, and that is why it runs slowly. So we put a lot of faith and a lot of trust in these, and they're excellent tools, but we simply can't run most of them for long enough to be able to check whether for these past climate tipping events they all run correctly. However, what we do know now is that at least the ones which run a bit faster mostly do capture the main feedback mechanisms or feedbacks that you need to be able to have tipping in them. So I would say I think the level of faith that we should have in our climate models with regard how well at least some of them seem to be representing changes in the subpolar gyre, the AMOC, and interlinkages between sea ice, the atmospheric forcing, and the AMOC is actually now substantially higher, in my view, than it was 10 years ago, because they have now reasonably faithfully reproduced the large tipping events of the past. And like I say, that's only been in the last years that that's been the case. So I think we have moved on in terms of having a lot more faith in our climate models. Sorry, that was probably a bit long.
No, thank you. That was very informative.
Okay.
I just wanted to throw it back to Tim if there's anything you'd like to add before I'm aware you have to run off at the hour mark. If not, I will thank you.
I'm going to try and hang in for 10 more minutes anyway, but let's move on. Ari,
Okay.
that's good.
Yeah, excellent. So we'll move on then, just picking up on this idea of crossing tipping points in the past. Curious to hear then perhaps from Tim and Louise, what have we learned from the past and what can this tell us about both where we are now and also what the future might look like on the current trajectory that we're on?
I can make a start. I think Louise nicely showed that evidence that we've got quite a bit of experience of tipping points in Earth's relatively recent past, even if it's against the background of sometimes a very different climate state. So we saw that during the last ice age, we've learned a lot about AMOC tipping points and their coupled consequences for the monsoons around the tropics. Simple thing is the AMOC is transporting a mass amount of heat from the southern hemisphere to the northern hemisphere in the Atlantic sector, and that's moving the ring of rainfall around the planet, which we call the intertropical convergence zone, northwards. So if you if you tip it off, you move that south, and that's the equivalent of stopping the monsoon intruding northwards in May, June into the Sahel. That will be a catastrophe, a humanitarian catastrophe today, because you're talking about a region, as Victoria is indicating, where there's quite a lot of tension anyway, shall we say, between settled agrarian communities and nomadic pastoralists. There's a lot of political tension, Boko Haram, other people like that. So I think it's quite easy to see what a catastrophe it would be if you lost that one soon. Equally, the one in India gets severely disrupted when the AMOC tips off, and that's, you know, over 1 billion people dependent on that in a sense. So that would again be a humanitarian catastrophe. We've learned some more, I suppose, yes, from the Holocene, the more recent bit of Earth history, where whilst we've seen variations in the great overturning circulation strength, and we've also seen some coupled changes of monsoons that have been linked to the rise and fall of past civilizations would be the simple version. There's plenty more gory detail to get into, but we'll have to wait for another time. There's some bits of recent history that are somewhat informative as well, because if you ask the question, why did Europe go from the medieval warm period to the Little Ice Age, and you can all picture the famous Dutch landscape painters' pictures of the snowy scenes of the Little Ice Age, the scientists' best answer at the moment seems to be that was some kind of as possible shutdown of the deep water formation in the subpolar gyre, or some kind of tipping point or shift in the North Atlantic subpolar gyre. So that might give us a clue, again, of the kind of impacts to expect, much more severe winters.
Louise, do you have anything to add? If not, I will continue and put it onto the rest of the panel.
I think Tim's covered all of that
Okay,
plenty well enough.
Yeah, so then that kind of leads me on really nicely, actually, Tim, to thinking about, we've heard about the tipping points, we've heard about how we're monitoring them, and what we can learn from them. But what might be the kind of, this is a question perhaps to put to Alex and maybe to Victoria as well, what might be the real life potential impacts of crossing these points on marine ecosystems, on fisheries, on coastal communities, and also thinking more broadly, of course, what happens to our global climate systems if things like, and I think we've just touched on this really, but the AMOC and the SPG were to be affected. Pass that to Alex.
Yeah, in terms of coral reefs, again, if we look back in history, there are what are called reef gaps, and these have occurred as a result of major phases of climate change in the Earth's Earth system, and are generally associated with major excursions in atmospheric CO2. Those reef gaps are inevitably associated with major phases of extinction in marine ecosystems. So, that the broad scale impacts on reef associated biodiversity are certainly possible and demonstrated from the Earth's history. But in terms of people, we kind of forget up in the north just how dependent many communities are around the world on reef-based fisheries, particularly if you're living in a small island, large ocean state in the tropics, where a lot of your food and certainly your protein and associated nutrients are going to be coming from fish and often from reef associated fisheries. So there are really significant impacts there. But even in general terms, we're seeing a shift in commercially fished stocks towards the poles and associated impacts on coastal states that are heavily reliant on fisheries as a result of that. We're also seeing conflicts developing as a result of changes in the distribution of those fish stocks, where nations can't subsequently agree on sustainable catch levels or how those sustainable catch levels are actually shared out amongst different coastal states. And we're seeing that in the North Atlantic, for example, with mackerel fisheries. So they're just some of the impacts that we're likely to see on at an ecosystem level and also on people.
Fantastic, thank you. Victoria, would you like to add to that from the kind of political governance point of
So,
view?
I did talk obviously a little bit about it in my presentation. So this socioeconomic impacts would range from rising food prices to rising food insecurity due to lost food production capacity, but also kind of to global financial and economic crisis, including governments defaulting on debts due to exploding costs for adaptation and disaster recovery, due to assets lost and so on. However, the specific societal impacts are really difficult to fully grasp and quantify because the ecological regime shifts would be so massive and so drastic on the one hand, but on the other hand, like, they will unfold over decades, right? So in a way, there is also a chance for people to potentially adapt. So the risk is kind of that although the shifts unfold over decades, the disruptions, of course, from the shifts will be felt straight away. Some of the, effects will be immediately felt. And so these disruptions may already overwhelm societies, right, in their abilities to adapt, and particularly if they are not adequately prepared, right? So if there is no governance already in place to prepare for that. And if, and particularly if also kind of if there are also other crises that they are facing, or if there are like, for instance, if these crises are exploited and these vulnerabilities and those disruptions are exploited by adversary actors, both internally, like, from some radical political groups, or externally, like from some geopolitical adversaries, right? Like, so we have also, of course, to think about the geopolitical tensions, like within which all this is unfolding. And so Laurie Layburn, for instance, and others have recently published a report on derailment risks, where they explore the risk of societies being overwhelmed by increasing climate change impacts. So, and that would, of course, include tipping point impacts. And how this kind of, being overwhelmed kind of derails then climate mitigation attempts, setting in motion kind of potentially a spiral where the resulting lack of climate mitigation leads to even further severe kind of climate change, even more severe impacts that even further destabilizes and kind of overwhelms societies, right? So we have kind of this kind of spiral in a way. And in a globalized economy, of course, the world impacts will always have global ripple effects, even like where like maybe the effects are more regional, right? And so this is like, this is why it's kind of important kind of to really have to kind of to try to start like, governance preparedness like early on, like, before we cross the really kind of dangerous kind of tipping points, and of course trying to prevent them in the first place.
Fantastic, thank you. So before we open up the questions to the audience, so audience, please, if you haven't already, you can start thinking about and using the Q&A function. Also feel free to ask generally or direct to a panelist if you wish. But yes, one more question to the panel, which is, following on from thinking about how these tipping points will potentially change our lives, what can be done either to mitigate or adapt to this? So I think I'll put this to Alex first, if you'd like to answer, and then we'll hear from some other panelists.
Yes, a good question. I think the first thing is emissions reduction is absolutely essential. At the moment, emissions are continuing to rise to an extent where, we are increasingly at risk of crossing these tipping points. So that's got to be number one. For coral reefs, the picture is very complex. We know that reefs that are under other human stresses, such as overfishing, eutrophication, say from sewage pollution and agrochemicals pouring into the coastal zone. We know that reefs that are under stress from these other impacts are more vulnerable and less resilient to the impacts of climate change. So, really trying to remove some of these other impacts on reefs is really important, to put them in as best a shape as possible to resist these climate impacts. But we are entering a situation which is so serious that we have to start thinking about things like, okay, if we're going to lose majority of reefs, where are reefs situated, which for various reasons of their geographic situation, they may be more resilient to these types of changes than in other places. And we know these areas occur, places where there's upwelling, so cooler water is pouring onto reefs, places where reefs are shaded, for example, by nearby cliffs, may be protected to some degree from climate change and so on. So where are these kind of what have been called almost hope spots that we should concentrate some of our conservation efforts on? Assisted evolution, so really looking at ways to improve the resilience of corals from the effects of rising temperatures, whether that is transplanting more resistant genotypes from one area to another, or thinking about genetic manipulation of the holobionts of both the symbiotic photosymbionts within the coral tissue, but also the corals themselves. So there's a whole raft of different things to think about here in terms of trying to get reefs through what is potentially on the near horizon in terms of changing conditions. And of course, another strategy is to actually start to collect coral species and preserve them ex situ. So to have these kind of aquaria where we're maintaining coral species in the hope that in the future we are able to improve the situation with respect to global warming, and perhaps the system becomes more suitable for growth of reefs again.
That's fantastic. Thank you, Alex. Really fascinating, especially what you're saying at the end there about preserving ex situ. I'm just going to throw over to Tim, aware that you've got some teaching to do, but is there anything else that you kind of like to add to that to wrap up your part?
Well, Alex has done a lovely job of explaining that there's always something useful we can do, even in the worst scenarios. But I wanted to emphasize, because a lot of people are asking in the Q&A where I'm frantically answering questions, what do we do about the sort of sense of doomism or despair or whatever that the prospect of these really dangerous, alarming outcomes would have for us. And my answer was kind of the journey I went on, which was to realize, hey, there are also what I'm calling positive tipping points that can accelerate the change we need in society and technology and all the rest of it towards zero emissions. We all clearly have a lot of skin in the game here, but we also have some agency, as we put it, as academics. We all, even just as sort of simple participants in society or consumers, can play a role in amplifying feedbacks that make the clean green technologies and behavioral options more attractive for the next person to adopt. So I kind of kept myself sane in all of this for the last however long by also studying those and realizing, hey, we shouldn't feel totally disempowered. It is up to us how we choose to act, and whether we want to, from the bottom up, be part of the movement that we need to seize a better future, and to limit the still avoidable tipping point risks. And for the ones that we won't avoid, we can still build resilience and manage. What's the phrase? We've got to manage the unavoidable. I think we can still just about manage it. But obviously we can't let this thing go too far. So those would be my parting words as I go off, sorry, to the audience and to the other panelists to teach my class about positive tipping points
No, fantastic.
this
Thank you,
afternoon.
Tim. Yeah, I would urge anybody who has not to take a look at that tipping points report, because it is, as Tim said, it's really filled with hope and proactive things that we can do. So yeah, I hope you inspire the scientists of the future this afternoon.
Thanks a lot, Ella.
Bye, Tim. Okay, perfect. I think we will move on now to our Q&A section. And Tim has quite nicely led us into kind of an answer to a question from one of our audience members, Noam, who has asked about whether we think that the messaging around kind of these tipping points is constructive, i.e., much of what the public have interpreted in the report is suggesting that the coral reefs are doomed, in which case they'd be rightly asking, what is the point of doing anything? So I think Tim's really nicely teed us up there. Do any of our other panelists have something that they'd like to add there in terms of messaging? And I guess that balance of we need to act now versus kind of optimism.
Maybe if I say something very briefly and then pass on to Victoria.
Absolutely.
Getting this balance between doom and solutions is really hard. I think we've got to be fairly brutal with the truth in terms of the very serious threat faced by what is the most biodiverse ecosystem in the ocean. And I think actually not delivering that message runs the risk that policymakers in particular think that, well, maybe it's okay to carry on as we are at the moment. Perhaps the situation is not as serious as we think. However, I think what is key is to demonstrate that, look, there are all these strategies here which can give us more time, can help coral reefs to get over this particular set of circumstances, that we can clean up our act in other areas to improve coral reef resilience. So I think the two messages have got to be balanced. I think we do have to really say it as it is. These are really serious tipping points. They have major consequences for the biological part of the Earth system and for humankind. But, you know, we have, and we're looking at solutions to these. The biggest ones, of course, which lead to reduction in emissions.
Thank you. Victoria, did you want to add to that?
Yeah, I just wanted to expand quickly on Tim's intervention on positive tipping points. I think one big potential of positive tipping lies actually in nature regeneration, including in expanding, for instance, marine protected areas. So nature regeneration can be positively tipped and can scale kind of sustainable carbon removal. And this positive tipping point in nature regeneration can itself be actually facilitated through positive social tipping points, for instance, in the spread of like nature positive and regenerative initiatives, through innovation in law, through empowerment of indigenous kind of communities who can then act as stewards of those ecosystems, or through social movements and civil society campaigning, who try kind of to spread kind of those nature positive narratives as well. And I think it's also like, and besides kind of those positive tipping points, as I think already emphasized, kind of this kind of building of system tipping point governance capacity is also very important. And we need kind of proactive capacity building and resilience kind of before those thresholds are held, kind of across. But I think for this, again, like, there's a lot of agency that people, like where people are like, ask kind of, so we need kind of, for instance, campaigns and civil society kind of to kind of put pressure on policymakers kind of to try to kind of develop kind of responses kind of to those risks, right? And so we've seen already kind of this happening and having positive effect, for instance, in Iceland. So Iceland, there, like the civil societies have actually rallied around tipping points and have kind of put pressure on their governments kind of to take this as a serious kind of risk. And Iceland is now, I think, the first kind of country who actually declared AMOC collapse a national security threat, right? So, which kind of makes it really kind of, basically forces the government to find responses and to prepare for this, right? So I think this is what we need kind of to see, and there's a lot of agency that people have, and where they need kind of to start kind of to acting and not kind of feeling disempowered. There's a lot we can still do. Thank you.
Fantastic. Thank you, Victoria. Next question is from Joel, who says, given the increasing risks and proximity of crossing multiple tipping points set out by the speakers, are we likely to see any reduction in future economic growth expectations when the next IPCC assessment reports come out in 2029? Or do we have an iron law of economic growth that's somehow immune to kind of mounting climate or ecological damages? I think I'll throw that one to Alex as well.
I think what the presentations during this session have demonstrated is that very clearly crossing these tipping points is going to have major economic consequences for humankind. We've got to remember the Dasgupta report here, where he pointed out very eloquently that our economic systems are based on the natural systems of the Earth, of the natural environment. And if we're causing major disruption to those systems, then the consequences of that are going to be major impacts on our economies and society in general. So I think that the kind of business as usual of kind of growth at the cost of anything else is something that we need to think very hard about. There are other ways of doing things. So circular economics or regenerative economic approaches are really important here. Victoria's already mentioned nature-based solutions, which can be very important, and solutions which are good not just for the climate, but also for biodiversity and for people in terms of employment and livelihoods as well. So our economy is so tightly coupled to the environment that really there is no getting away from the fact that these tipping points are going to have major impacts on society.
Victoria, would you also like to say a few words on that one? Thank you, Alex.
No, I think that's kind of basically builds on what I said before. So I think that's
fantastic. Thank
I
you.
agree with Alex.
In that case, we've had actually quite a number of questions asking Ben if you can please expand or give a little bit more detail about kind of what caused this shutdown in the 2009-10 and just a bit more about the science behind that.
So the AMOC itself is not just driven by those density changes where that dense water gets mixed down in the subpolar region and around Antarctica. It's also driven by the wind. So the wind in the Southern Ocean blowing around Antarctica drives water to the north. And what we see is that potentially at 26 North between the Canary Islands and Florida, the AMOC is more sensitive to the wind on the surface there than it is perhaps within the subpolar region. So what happened in 2009-10 was actually it was a natural event. We don't think it was anthropogenic in nature. It's basically the wind reduced in the North Atlantic, the wind patterns changed, and actually that it went to a period where the wind has actually reversed around that subtropical area. And what we saw was this downturn in the AMOC. But it was also, there were changes in the structure of the ocean there, because at 26 North, there are deep currents coming back and there are other surface currents going northwards. So it's a bit like a sponge cake in a way with different movements of ocean currents. And what we saw was a weakening of those southward currents as well. So essentially, it was a natural event.
Thank you. I'm going to pass on now, I think, to Louise. We've had a question about geoengineering. I think I'm going to let you take it away on that one and talk a little bit about geoengineering in our polar regions and kind of how that has a knock-on effect in the rest of the world.
Sure. I'm not sure I have the exact question in front of me, but I think it is a really interesting topic at the moment, this idea of, given that humans have had such a massive impact on climate, whether we should do it in a more purposeful way or not as well. So, I mean, in some sense, the Protestant sense, I would say the biggest geoengineering intervention we could make is to stop putting carbon in the atmosphere, right? Like, if we actually stopped right now, then there will be no more warming. There's actually, it stops warming dead. And that is the biggest thing that we could clearly do to stop our movement towards tipping point. So I think that, at the risk of stretching the definition of geoengineering, is the most obvious thing to do. Beyond that, I was just going to say there has been talk about, in some of the other questions, about reversibility and such like. So I think the nice example for this geoengineering discussion is perhaps the sea ice. So sea ice is often not treated as a tipping point because it's actually, most of the changes we see in, say, the Arctic sea ice are potentially reversible. So if the amount of carbon in the atmosphere comes down, then it will actually not exactly follow the precise same pathway down, but it's probably not really, that's why we don't really talk about the Arctic sea ice or the summer ice as exactly a tipping point. But there has nevertheless been some emphasis put on whether we should be considered geoengineering for the Arctic sea ice. That's partly because the amount of sea ice we have also has a big impact on the rest of the global climate. So it helps cool the Earth and potentially helps reduce the risk of major loss of Greenland ice and also potentially major changes in rainfall systems and droughts and other knock-on climate consequences that none of us want. So I was just going to comment on the sea ice geoengineering scenarios which have been examined. We can relatively easily examine these sorts of things in our climate models. So you can see from this sort of thing that there are things that could be done, but the problem is most of the things that could be done to sea ice would be so expensive and require so much engineering that they would really not be fit for purpose. So the types of interventions that has been talked about in terms of adding additional water and freezing that on top of the sea ice is quite hard to see how on a very grand scale across the whole of Arctic it would be possible to implement these. That's not to say, because some tipping and some impacts are more regional in scale, it's not impossible that on some smaller regional basis that there might be the point to do some very small scale climate interventions on the sea ice. But it is I find it personally quite hard to see how that could be useful. And I think that's even more so true for things like solar radiation management, where the knock-on impacts would appear to be so strong that it probably is. It's hard to see how there will be a case where it's not more risky to do that than it is to try and decarbonize faster. So that is at least my own personal viewpoint on it, that it's interesting for climate scientists and modelers probably to explore some of this, particularly in model world where there's no real world impacts, just to see, and particularly maybe to explore whether it could help mitigate, because tipping points are both global scale, but also sometimes regional and small scale. So maybe to look at smaller scale and particularly nature-based solutions are probably usually preferable.
Yeah.
Thanks.
Thank you, Louise. Yeah, the question was quite simply, has the panel any views to offer regarding geoengineering? So you've answered that perfectly. Thank you. Also, just to pick up on what you've just touched on at the end there about decarbonisation, maybe I'll pass over to Alex if you'd like to touch at all on kind of marine carbon dioxide removal and any of those approaches that we have available.
Yes, absolutely. MCDR, or marine carbon dioxide removal, is essentially geoengineering as well. It comes in a number of forms. One of them is, for example, growing huge quantities of seaweed, so kelp, and then dumping it in the deep sea. That's a kind of form that is based on, I guess, almost a natural solution, but taken to a huge scale. Then there are kind of more solutions more in the area of kind of chemical manipulation of the ocean, and alkalinity adjustment is one of these, where you're trying to add alkaline substances to the ocean and adjust the carbonate system. Now, the issue with these, and the issue with all of them, is that we have very little understanding of both the effectiveness and the impacts of undertaking such manipulations at a really large scale. So we need to do a lot of work as scientists to really get a better understanding of how effective these measures are actually going to be in drawing CO2 out the atmosphere, but secondly, what the consequences of these types of actions might be if undertaken at really huge scales that would be needed. And of course, there are a variety of other questions around the economics of doing this and so on. Now, the big worry, I think, that I have as a scientist, and I'm sure many other people out there have as well, is that as we become more desperate to do something, then MCDR may be seen as a solution that investors will throw money at. But really, we've got to ensure that decisions made around undertaking such measures are knowledge-based. And to do that, as I said, the scientific evidence has to be there to understand effectiveness and potential negative consequences of undertaking these actions.
Thank you very much, Alex. I think we will just have time for one more question. Victoria has also answered that question in the chat, in the Q&A, if anybody else wants to, if any of the audience want to go and have a look at what she has said. We will squeeze one last question in, which is, how can ocean literacy be scaled to translate these complex tipping point risks into simple, actionable narratives for the public, ensuring that communities, policymakers, and financial institutions all grasp the stakes and act on resilience pathways? I think that's a really good note to end on, kind of what can we do about this right now. I'm going to open that up to the floor. Perhaps Alex, you do want to start off, but I'll also we'll just squeeze that in the last 3 minutes.
Yeah, I think my view on this is that it's very interesting. I wrote a book that was published in 2019 called The Deep, where I did discuss quite a bit about climate impacts and also impacts of other things like plastic pollution and so on the ocean. And during the public presentations on the book, I always had the same question, which was from the audience, which was, what can I do in my personal capacity as a member of the public to do something about this? And I think this is a really important point in terms of ocean literacy, to ensure, to kind of counter the doom, is to really make people understand that they can do things in their everyday lives to improve the situation in terms of climate. They can look at their energy consumption, they can look at their lifestyle, they can look at volunteering and getting involved in projects around nature-based solutions, and really letting people know that they can do these things is a very important activity in terms of education around this area, what we call ocean literacy. And of course, that can be tailored for different cultures, different societies, societies which are, very well off, such as many countries in Europe, compared to societies which are based in low middle income countries as well. So I think this is a really important point and something we need to do more work on.
Yeah, thank you, Alex. Ben, I'm just going to pass to you. I know you do a lot of work in ocean literacy, and we've worked together in outreach and engagement. So yeah, what would you like to add to that?
So Alex covered that really well, but I would just like to say that we don't write a report and then that then goes to policymakers. We engage with policymakers to try and make it understandable or make the key points available for them. So we work with a whole range of stakeholders, from policymakers all the way through to young people in schools. And I would just chip in that we go into schools and sometimes you can be a bit, you don't want to take a doom and gloom message to them. So you can just say to the young people, well, what do you know about climate change and what the impacts are? And what you get back is so incredible. They're so well educated. And again, that is the next generation coming through. But also we can not just work with politicians, policymakers, we work with artists, poets. We get the people who can really get ideas across to the public. And that is the sort of building block. That's the foundation of where we should go from as well.
Fantastic, thank you. I like that as an ending sentiment. So I think that will be our last question. So just to kind of conclude what we've chatted about today, we've heard from experts in ocean and climate research. We've learned that when we think about climate change, it's not just about the terrestrial world. We've learned that when we need to include kind of the ocean and all of the systems that surround our ocean. And how important the ocean is, not just in regulating and buffering, but also in preventing us from reaching these crucial tipping points. We've spoken about the science and the technology behind how we know what we know about these systems and just how vital it is that we continue to make these long-term ocean observations and improvements to climate models. We've seen in some cases how we've already reached these tipping points, or if not, they're not far away, and thought about how these may take decades or even centuries to recover, and that it's the decisions that we make now and the action that we take today that will impact our future generations. And finally, we've delved really into what we should do in terms of reducing emissions and decarbonising, and how the ocean can actually help us to mitigate some of these climate impacts. So with that, I would like to thank our 5 fantastic panelists, Ben Moat, Louise Syme, Alex Rogers, Victoria Speiser, and Tim Lenton for your time and expert contributions. It's been a really insightful and enjoyable discussion today. Thank you also to Lana Young at the NOC for overseeing the organisation of this event. A huge amount of work has gone on in the background to get us here today. And so thank you for just being a joy to work with. As ever, thanks to Katie Mitchell and the organisers of the Virtual Ocean Pavilion. It's just incredible that we can make discussions like this so accessible for so many people. And of course, thank you to our wonderful audience for your attention and your engagement and your fantastic questions today. I know we didn't manage to cover all of them, so please don't hesitate to follow up with media@noc.ac.uk if you would like to continue the conversation. So with that, we will conclude the session and wish you all a brilliant rest of your day. Thank you.